Hello everyone, welcome back to our course on Mechanical Behavior of Materials Part 2. So in the last lecture, we discussed about the calculation of the theoretical strength, and then we observed that there is a discrepancy between the theoretical strength and the stress we calculate in the lab, right? Or practically we obtain. So typically it is in MPa, but the theoretical strength is in GPa, right? And then I mentioned that this discrepancy is mainly because of the two reasons. One is your dislocations, presence of dislocation, which we have already discussed in the course 1, Mechanical Behavior of Materials Part 1. And then I mentioned about the presence of other defects such as cracks and porosities, right? And this led to the genesis of fracture mechanics. And then I also introduced the term of stress concentration, where we were talking about the stress-based approach or Inglis criteria, right? And the another one is your Griffith criteria, which is energy-based approach. So in today's lecture, we will talk about the Inglis criteria or stress-based approach in fracture mechanics. Okay. So let's start lecture 2 is stress-based approach. Okay. So let's first understand what do we mean by stress concentration. So let me draw a plate. And then I'm drawing some imaginary lines. We have light stress as sigma. Okay. And now I'm drawing some line of forces, or in some books you're going to see that it is also called as stress trajectories. Okay, so what I'm doing in this plate, when we have sigma as applied stress, I'm distributing it with these lines, some imaginary lines, and we call these lines as a line of forces or stress trajectories. Okay, so I can draw many lines like this in a given plate. Okay, now let me introduce a crack or say hole or porosity here, and let's see what happens to this line of forces or stress trajectory. So I have the same plate, but let me now magnify it a bit so that you can understand it better. So I'm just increasing the size of the plate. And I am introducing now a crack here. So this is the crack. Okay. We are in the same sigma. So applied stress doesn't change. Okay. Let's say width is also not changing. I am just magnifying this image left on the left. On the right side, I'm just magnifying it for better understanding. So width also doesn't change. Now let's see what happens to the stress trajectories. So let's say I'm now taking this point number 1 here. Say this line number is 1. And we can do this for all the line trajectory lines or line of forces on the left side, right? Remember, you have this crack is an empty space, it's air, so it cannot sustain any load, right? So all these trajectories as soon as they see the presence of crack or porosity, some voids in the material, and we know that they cannot take load, so they are going to deviate, right? So you are going to see the line of forces becoming something like this. So there is a deviation in the path. Why? Because this particular crack here, this cannot sustain this load. So you can see here it was a full material, then the line number 1, but now there is a deviation, right? And you can do this for all these lines. Say this is line number 2. Similarly, line number 3. And you can repeat it. Okay, and so on. So you can have now line away from the track tip is going to just go like what we have seen in the left image. So far away from the track tip, there is no deviation. That means there is no effect of the presence of the track. So far away from the track tip, it is going to behave like there is no track. Okay. So here you are going to have uniform distance. What we have in the previous case without any track, right? And what you see here that all these line forces have been squeezed in this particular area, isn't it? Right? Because the track is the track cannot sustain the load or the stress trajectory. They are going to bend in front of the track tip. So there is a squeezed region. Okay. So this is number 1 observation that the line forces are squeezed. The second observation, if you see, the distance between the lines is much finer at the thread tip, and as you move away, it is increasing, and finally it becomes like there is no crack in the material. Right? So you also see bending here in this region. But the bending, the strength of bending or magnitude of bending is much smaller than what you observe at the crack tip. Okay, so the distance between the lines, these imaginary lines. Again, remember these are imaginary lines, right? So the distance between these imaginary lines is higher. Okay, as you move slightly away from the crack tip. Okay, now third observation is, so you see there is a strain energy release. This part is not taking any load, right? So there is a release in strain energy here. We are releasing the strain energy, okay, in this part, and we are going to utilize this concept when we talk about the Griffith criteria. Okay, so overall, if you see, we can let me write down the some of the observations what we have discussed. Okay. So the local stress is proportional to the spacing between line of forces, or we call it stress trajectories. Okay, so higher the spacing, then the concentration is going to be lower. right? What does it mean? It means that in the squeezed region, you're going to have stress concentration. Stress is concentrated in that particular region. So the local stress is going to be higher at the crack tip. And as you move away from the crack tip, your local concentration or stress, local stress value is going to be smaller, right? And as you move away from the crack tip, it is going to be equivalent to the applied stress, which is sigma here. Okay, so that is one. Now other observation is, since the tensile stress cannot be transmitted through a crack, the line of forces are diverted around the crack. Okay, and you have seen that the line number one, you can imagine it was coming down, it saw the presence of a crack, so it is going to get diverted, and then get concentrated in front of the crack tip. Now, this is going to lead to the squeezed region. And you can see the line, if you just count, just imagine it, count the number of line of forces in front of the crack tip, right? It's going to be much higher than if there was no crack, right? At the same position, right? That means you're going to have stress concentration now. So if the applied stress is sigma, you're going to observe a stress value which is higher than sigma at the crack tip. Okay, so this leads to stress concentration. Okay. So the presence of crack has resulted in the stress concentration in front of the crack tip. Okay, so even if the applied stress is sigma, it can be much higher than the sigma value. This means there is a possibility that the local stress in the front of the crack tip is equivalent to the theoretical strength we calculated, right? So if that is the case, locally it is going to fracture, isn't it? And that is what we discussed, right? That there is a discrepancy because one of the reason was dislocations and another one is crack, right? So whenever there is a presence of crack, locally you're going to have stress concentration, and this stress concentration can lead to a value of stress at the crack tip which is much higher than the applied stress. Okay, so even if the applied stress is lower than yield point, locally it can be higher than yield point, even it can go up to the theoretical strength value, which can lead to the fracture. Okay, so even if the sigma is in MPa, locally it can be in GPa. Okay, and that is the whole concept of stress-based approach. Okay, so overall, if you see, you can write that due to the presence of crack or in the presence of crack, leads to attenuation of stress, to cohesive stress or theoretical stress what we have calculated. of say brittle material. Okay, so locally you're going to increase the stress. That means there is a stress concentration locally, which can be a very high value, even the theoretical stress value, and then it can lead to the fracture. So this is all a fundamental understanding, visualization, somewhat qualitative, right? So what Griffith did, Griffith gave a quantitative analysis to this phenomena. Sorry, not Griffith, Inglis. I missed. So Inglis gave a quantitative analysis. That was in 1930. So he proposed a quantitative analysis of stress concentration. Okay. So now let's assume that you have a plate which is infinite. And I will tell you what does infinite means. And typically, whenever we mention an infinite plate, we will make something like this, some wavy structure. So you have an infinite plate, and then you have a through thickness crack or elliptical hole in this case, right? So you have elliptical hole in an infinite plate. Now this term infinite plate I am going to use for some of the lectures. It means whenever we say something is infinite plate, it means 2 points. First, stresses due to the presence of or stresses at the hole is not influenced by the boundaries, right? So stresses at the hole. So this is your elliptical hole, right? Are not influenced by the boundaries. So these are your boundaries. Okay. So whatever stresses you are going to observe, say in this region, they will not be affected by the boundaries. That is point number one. And second, the dimension of the hole is much, much smaller than the dimension of your plate. And dimension of the plate we can denote in terms of width, right? Width of the plate. So hole is much smaller than the plate width. Okay. So it means W is much higher than 2A, where W is your width of the plate and 2A is the length of this elliptical hole. So let me just draw the hole here now. Suppose this is your hole, same one, right? So this one we will denote as a 2A. Remember that. It's not A, it's 2A. Okay. So whenever we give you numerical, I'm going to mention A or 2A. Or if I say it's a central crack, then you should know that this is length is given as 2A. And all the formula you are going to see eventually will have A. So you need to know the difference between 2A and A. Okay. So whenever you do assignments, please be very careful about it. Okay. And height is say 2B. So you have an elliptical hole. Height is 2B and length is 2A. Okay. So this 2A is that. And then you are having stress here as sigma. Okay, and this hole is through thickness hole. That means it is going through the thickness. So if you see a plate, you can see the hole from this side and you can see the hole from the opposite side also. So through thickness hole or through thickness crack also. That means it is going through the thickness. Okay. So overall, if you see the Inglis assume that it is an infinite plate. That means the stresses at the hole are not influenced by the boundary, as well as the plate width is much higher than the length of the crack. Okay. So the formula he proposed at the crack tip for stress. So stress at the crack tip, if I denote this as sigma tip, it will be sigma tip equal to sigma 1 plus 2a by b. Okay. Where sigma is your applied stress, and we also call sometimes sigma as far field stress. Far away from the crack, right? So far field stress or also applied stress. Okay. Now, if you see this equation, applied stress is sigma, and then you have a factor of 1 plus 2a by b, right? Which is going to have some value, okay, and which is going to be also higher, more than 1, because it's 1 plus 2a by b and it's an elliptical hole, so 2a is going to be higher than b also, right? So overall, if you see at the crack tip, the value of sigma tip is going to be higher than the applied stress. So just now we learned the qualitative way. Now Inglis gave a quantitative approach to the whole concept of stress concentration and proposed a formula for sigma tip, okay, or stress at the crack tip. Okay, so what is stress concentration factor? Okay, so if I denote this as KT, this is going to be sigma tip by sigma. Sigma tip is the stress at the crack tip. So if you have a crack, the stress here, so this is your sigma tip, and sigma is the applied stress far away from the crack, right? Or elliptical hole, whatever. Okay? So that stress is far field stress, that is sigma. Now suppose this elliptical hole becomes, sphere, circular, right? So 2a is equal to 2b, right? So if you see the formula, sigma tip is sigma 1 plus 2a by b, okay? And if I take a circular crack now, so this is your circular crack. Here 2a is equal to 2b. So this particular equation, now if I use this circular crack instead of elliptical crack, this will be sigma 1 plus okay, sorry. So this will just cancel. So it will be 3 sigma. Okay. So 2a is equal to 2b, that means a equal to b. Right. So I'm just replacing b as a. So this gets cancelled out. And then sigma tip equal to 3 sigma. That means if I apply say 10 MPa and you have a presence of circular hole, right? At the tip of the circular hole, your stress is 30 MPa. So it is being magnified. And that is the concept of stress concentration. Right? Okay. Now imagine if you increase the major axis, right, related to B. Okay, so you are increasing continuously the A value and you are relatively to B, which is higher. The electrical hole is going to become a sharp track and it is going to have some curvature, right? Say rho. So what is the formula now? So as major axis increases relative to B, the elliptical hole becomes a sharp track. Having a radius of curvature at tip equal to rho. Okay, so increasing continuously A, so it is going to become a sharp crack with a radius of rho. So in this case, sigma tip can be in a sigma 1 plus 2 root over A by rho. Okay, because we know rho is B square by A. Okay, so I'm just replacing B in terms of A and rho. So this is your equation here. Whenever you have a track having a curvature of rho. Okay. So for circle, again, if you see A is rho, right? Because the radius of curvature for a circular hole is your rho, A, right? So in that case also, if you see A and rho will get cancelled out. So sigma tape will become 3 sigma, which is equivalent to what we have just discussed. Okay. So for circular case, A is equal to rho. So sigma tape becomes sigma 1 plus 2. So 3 sigma. So same. So it is same as this one on the top. So it validates, one way of validation. Okay. Now if the track is very sharp, so for very sharp track, we can write rho is much less than A, right? Because it's very sharp, so radius of curvature is very small. So we can write as an approximation sigma tip as 2 sigma root over A by rho. Okay. Now see, A here is not the full track length. Huh? A is your half track length. So again, don't make mistake. A is different than 2A. Okay. So 2A was the full track length and half track length is your A. Okay. So this is the stress at the track tip because of the presence of stress. Okay. And it is related to the track length as well as the curvature. Right. So overall, if you see, the stress at the track tip is going to be dependent upon the size of the track, which is in this case A, as well as the curvature of the track, right? If the curvature is higher, then sigma tip is going to be lower. And if the curvature is smaller, then the sigma tip is going to be higher. Similarly, if you increase the track length, your sigma tip is going to be higher, and which makes sense, right? So suppose, let me give you a qualitative way of understanding what happens when you increase the track length, right? So suppose you have a width of same width, two plates I am taking, and let's say the width is same W. Okay. Now if I introduce a crack here and then another crack of higher length, right? Now if you remember the concept of stress trajectories or line of forces, right? And if I just do the same concept, apply the same concept of with these all these lines here, and applied stress is also same. So I'm keeping width the same, sigma is same. Only thing I'm changing here is the crack length. So what is happening, right? So if the sigma is same, the number of trajectories, right? All these imaginary lines, it is going to be same. Okay. So let's say same number of trajectories. Okay, and all these trajectories are say coming down and they see, oh, there is a presence of crack, right? So if you just visualize it, what you are going to see, the number of line of forces is going to be much higher here, right? Because the number of line of forces, the way they are going to deflect is going to be much higher in the case number 2 than case number 1, right? That means the stress concentration in the larger crack is going to be higher. This is the visualization, what we are doing, right? What English did is he gave a formula, right? Which is 2 sigma root over A by rho. So now you understand the qualitative way of understanding with respect to the line of forces as well as the quantitative way given by English of stress concentration. Okay. So overall, if you see, the stress concentration is going to be depending upon the crack length, depends upon crack length as well as shape. Right. So sharper the crack, higher the stress concentration. Sigmatic is going to be higher. You see the above formula. That means if you have a elliptical hole and crack is going to give you higher stress concentration. And the third is sigma tip is the maximum stress. Okay. So if you see the plate I've drawn here, sigma tip is what? Sigma tip is going to be the stress here, right? Sigma tip in both cases. So in this particular plate, the highest stress what you observe is the sigma tip, which is at the crack tip. Later on, I'm going to show you the profile of the crack, stress at the crack tip, stress at the crack tip in the crack plane, etc. Okay, and you will see there also that the sigma tip is going to be the highest. Okay, so these are the 3 points we can note down based on the English criteria. Okay, now what happens when sigma goes to 0? We can imagine, right? Sigma tending to 0. So the stress at the crack tip is going to be infinite, right? That means if I have a crack which is very, very super sharp, right? So that it is tending to 0. As soon as you apply a load, it is going to fail because the sigma tip, the stress at the crack tip is infinite, right? It doesn't happen like that, right? Okay. So what is happening? What is the minimum curvature you can observe? So if you see the bonding, the minimum curvature will be in the order of R0, right? The distance between the 2 atoms. Okay. So if I explain it, so I am trying to say that if sigma rho tends to 0, sigma tip tends to infinite. Okay. So for infinitely sharp crack, sigma tip is going to be very, very high. Very, very high. And that is what I've been saying, that it can go to the theoretical strength also, and then it can lead to fracture. But no material is there which can sustain the infinite stress. That means as soon as I applied the load, it is going to fail, right? But in real situation, if you see if I just draw the structure what we have seen before, suppose this is your atomic structure, right? So this is what I was talking about. So this area is your track here, right? So the minimum curvature, what you observe here. So this is your crack profile. So the minimum curvature will be in the order of R naught. Okay, not 0. So there will be some value of sigma t. It is going to be much higher. I agree, but it is not going to be infinite. Okay, and actually you can calculate that now. So what I was saying that for brittle material, minimum static radius will be in the order of atomic radius or distance between the atoms, atomic distance. Okay, so let's assume that rho is equal to R naught. Okay, and R naught I have already mentioned, it's an interatomic distance. Okay, so if that happens, let's calculate what could be the fracture stress there. Okay. We know sigma tip is 2 sigma A by rho, and rho here we are replacing by R naught. So sigma tip becomes like this, where sigma is your applied stress. Okay. We also know what is the theoretical strength, if you remember. This is E gamma by R naught. Okay. Now this material is going to fail if sigma tip becomes theoretical strength, right? Then that bond is going to fracture. So let's equate the sigma T as sigma TH. And sigma TH from this equation now we can write root over E gamma by R naught to sigma A by R naught. Okay. And so here R naught will cancel. So let me replace this by rho for now, because if it is equal to R naught, then it's fine. If let us put it in a general way that rho is in the order of R naught, we don't know yet. Okay. So now sigma can be written as root over E gamma rho by 4 R naught A. Right? Okay. Or we can just write as sigma fracture, because we have replaced sigma tip by sigma th. So you can actually calculate what is the fracture stress for brittle material. Later on, I'm going to also talk about the ductile material. So in ductile material, typically because of the plastic deformation, your crack tip is going to get blunted. Okay, so your rho is going to be much higher than R naught, much higher than R naught. Okay, for brittle material, there is very less or approximately no plastic deformation. So rho is in the order of R naught. So the formula what I have derived here is basically for a brittle material. It is easy to derive the equation of fracture stress for brittle material, which is given something like this, which is related to E gamma rho by 4 R naught A. And if you know the rho, you can calculate actually the fracture stress. Okay. Okay. So now we have understood the concept of stress concentration. Okay, and it is happening now because of the presence of track, elliptical hole, circular hole, porosity, whatever. Some defects are there, and because of that, there is a stress concentration. Okay? So let's solve some numericals to understand further. So suppose you have two plates. Uh, Plate one, and then you have a circular hole here, and another one is okay, and you have elliptical hole here. So you have case one, case two. Case one is circular hole, case two is elliptical hole. Let me put some values, and we are having a applied load of 10 kilonewton in both the cases. The width and thickness remain same in both the cases. Let's say 10 millimeter. Width is say 3 millimeter. Okay. So I have fixed applied load 10 kilonewton, then I have fixed the dimension also. Both are same in both the plates. Only thing I have changed here is the track, uh, uh, the hole, right? So in one case you have elliptical hole, in one case you have circular hole. So let's see, the circular hole has a dimension of say 2 millimeter. Okay. So I am again fixing or making the major axis as 2 millimeter, same as the circular hole. Okay. And this one as 1 millimeter. Okay. So now interesting, right? Dimension is fixed or same for plate. Load, applied load is same for both the plate. Only thing is the configuration of the hole is changing. That too, I have made the same length. The major axis here in the diameter here. Okay. So let's see quantitatively what is happening now in terms of stress, right? So sigma, which is the far field stress or applied stress, can be calculated by load versus area, right? So area is this one, which is 10 into 3. So 10 kilonewton, which is 10 into 10 to the power 3 divided by 10 into 3, right? And if we calculate approximately, it will be 333 MPa. So applied sigma of far field stress is 333 MPa in both the cases. Okay. Now let's see case 1, which is the circular hole. Okay. So sigma max, which is equal to sigma tip. I have already mentioned that the maximum stress is going to be at the sigma tip or at the tip, right? And this is sigma 1 plus 2a by b. And for circular hole, this is 3 sigma. We have discussed this. Okay. So sigma max in this plate 1 is going to be 999 MPa approximately. Okay. So in this whole plate 1, the maximum stress you are going to observe is 999, and that is going to happen at the tip of the hole, circular hole. Now let's see case 2, which is the elliptical hole. So here also, what is the maximum stress? That is going to be at the tip, and it will be same equation, English one. Okay. So sigma 1 plus 2a. So here let me write 2a is equal to 2 millimeter and 2b equal to 1 millimeter, right? So 2a equal to 2, and then here it is 1 by half. So 5 sigma. Okay. So sigma mass is 5 sigma, and this will be 1665 m. Okay. So what do you see? Keeping everything same, I'm just changing the configuration. So the circular hole is 999, and if I make it ellipse, it is going to increase because it is going to more go towards the track. Okay, that is observation number 1. Observation number 2 is what is the applied stress? It's 333 MPa. Now, because of the presence of hole, we are going to attenuate the stress, right, locally at the crack tip. So in one case, it is 999, see 3 times higher. In another case, it's 5 times higher. So a stress concentration, right? You're going to see the stress concentration at the crack tip. That is observation number 2. Now, if I give you that, hey, my the plate or the material of this plate has a yield stress of say 300 MPa, or say 400 MPa, right? Yield stress. Now, what is the applied stress? 333 MPa. So ideally, I would say, oh, it is not going to plastically deform, isn't it? Because the yield stress is 400 MPa, but the applied stress is 333 MPa. But remember, locally, you're going to have a stress which is much higher than 400 MPa. So the question is your material is going to deform? This case 1 and case 2? So answer is yes, right? Because although the applied stress is less than the yield stress, which is 400 MPa, locally your stresses are much higher than 400 MPa. So you're going to get plastic deformation locally. Okay, so this is another observation. So overall, if you see the stress-based approach, right, we have discussed about the qualitative way as well as quantitative way, and the conclusion is that there will be a stress concentration at the crack tip. The maximum stress is going to be at the crack tip, and it is going to be higher than the applied stress. And if that happens, there is a possibility that at the crack tip, you are going to go to either, since it is higher, it can be more than the yield point, or it can also go to the theoretical stress. So if it is more than the yield stress, it is going to get plastic deformation. And if it is higher than the cohesive stress, it is going to fracture right away. Okay. So that is what is all about Inglis criteria or stress-based approach. Okay. So in the next lecture, we are going to start talking about the energy-based approach, which is Griffith criteria. Okay. Thank you.